Or we have, let me know when you're ready.
Ready?
Sorry.
We'll go.
Do you want me to start?
Yeah.
Okay.
We're 10 minutes late.
Yeah, we're 10 minutes behind, but that's all right. We're gonna catch up. I don't know. We probably won't, but we'll do all right. Anyway, we're going to continue in this vein of learning more about structure. With my first NPA meeting was 4 years ago in Albuquerque, and one of the people I got to meet at that time was Bill Hohenberger, and he gave me one of these baseballs, which he's going to show you later. And I just remember spending so much time being so fascinated with it, and he let me take it home with him, and I still have it. I love it. So Bill and I have gone back and forth on a number of things. He's just a very creative guy. He keeps coming up with just new ways of looking at things, and he says since he wrote his paper, he's got 3 or 4 new ideas. So I don't want to take any more of his time. Bill Hohenberger, come on up.
Thank you. I'm glad to be here. It's hopefully somebody will gain some insights from some of the things that I present here. What I'm going to do first is go through a very quick review of some of the papers and some of the things that I worked on. Over the last few years. The first I'm going to go over is the structure of ether and charge. Obviously, I'm an etherist. I'll talk about electromagnetic waves, the quark ball that Greg just showed you. Then I'll go into fractals, Sierpinski's triangle, and then finally talk about what the paper's about, which is electron structure, proton structure. This is my concept of what ether is in my mind. I see it as 4 loops in an octahedral structure, and it's elastic in nature. I'll show you, this shows you a better idea of what one individual cell would look like in the ether. And what I'm saying is that when the cell is imbalanced in the center, there's no charge. When it's stretched out and it's in tension, there's a positive charge. And when it's collapsed, it's a negative charge. So we have an elastic ether that can flex with both positive and negative charge. Then I'm going to talk about oscillatory systems. Whether you look at pendulum, water waves, sound waves, or a clock, an oscillating system always oscillates back and forth from static energy to dynamic energy. In the case of an electromagnetic wave, it would be from charge to spin. And they're 90 degrees out of phase with each other. It requires 2 things. It requires a medium, and it requires some mass for it to oscillate. I am therefore proposing that an electromagnetic wave is a rotary oscillating system. If you were to go back and get an old mechanical clock with the old timing spring that was in there, and it just sits there and goes back and forth like this, that's what I think an electromagnetic wave is. The only difference is, in a clock, the electromagnetic wave is on a fixed axis. Here, it's propagating forward. So it's the same thing. This is a vision of what I see, 2 different types of electromagnetic waves. The top one is just a natural oscillating wave, and if you can see the arrows right there, one spinning one way, it winds out, then it winds down, then it winds all the way down, and then it winds back. So you have a case where it winds up, winds down to neutral, then winds all the way down, and winds back, and it's just like they're going back and forth. The second wave is the one that's past saturation. And the difference between the 2 waves depends back at the point of origin. It's how did the wave get created, what made the wave. So like if you're talking about a boat going through the water, it makes a wave that spreads out from the boat. If you drop a rock in the water, it's a circular wave. So this is the same thing. The difference here is the frequency. I believe it's the electrons spinning that make the electromagnetic wave. It grabs, there's some kind of a coupling coefficient with the individual energy cells in the ether, and it twists the ether. So it's actually coupling with the ether and twisting it. And when it's twisting slower than the natural propagation speed, you get the top wave. On the bottom wave, it's twisting faster. You're at higher frequencies. And so it's like push-pull. You're pushing the wave out, and then you're pulling back on it before it gets its chance to oscillate all the way out. That creates a stretching mechanism in the center. So that's what these black areas are. You push the wave out of the way, and then you collapse real fast, and you're starting to stretch the ether and create a negative charge. Then what I did is dissected the wave. When you look at a pendulum, you see you have the spin and the force vector, and they're 90 degrees out of phase with each other. There's a natural 0 point on these wherever they cross the 0 threshold. So that's where those lines are lined up, right there. So that segments the wave into 4 individual segments. So each one of those would be a burst of energy that would come through. And then below it you'd have 4 more, which would be the counter, the yin and the yang, the up and the down. It's the opposite effect of the top loop. So that's what I'm doing here. I'm breaking down these and I'm showing different kinds of loops, the direction of the spin, and I'm showing how the loop is starting to break apart, and you're starting to see areas where the ether is condensing and areas where the ether is being stretched out. Then I went through a long, laborious process of trying to decide what those were. I finally came up with this arrangement down here. I'm saying these are quarks. I'm saying quarks are not particles. Quarks are charge and magnetic vectors. They're field structures, and they are contained within the electromagnetic wave. That's why you can never isolate a quark. You also, when you do this, you don't need gluons anymore, because now you can superimpose field structures on top of field structures. Then I started looking at the spins, and that's how I developed this ball right here. I was looking at the spins. I came to the conclusion that RGB stood for polar coordinates. That's why you have to have 3 of them. You have to have 3 quarks, 1 in each direction of the 3 polar coordinates. So that, actually you need 3 waves then. So when 3 waves are coincident at a point, where if you have 3 down quarks coincident, you create a DDD. That's what you see right here. So I was looking at relative spins. The red line on the ball is the polar coordinates. There are 8 segments. And I was looking at relative spins, and if this one's spinning this way, and that way, then the spin axis would be here. So that's how I established this point. Then I said, well, what happens now if I'm into the next phase of the electromagnetic wave, where it's unwinding instead of winding up? Well, that came over here. So if you go back to the wave right here, you see 8 segments, 4 up above and 4 below. You see the same thing here. There's 1, 2, 3, 4 quadrants up above, and there's 4 quadrants below. And if you look at the location of the quark vector fields, I don't want to call it quarks because then you think of particles. These are quark vector fields. If you look at that, it matches exactly the arrangement there. You start, if I turn this right, there's up, so it's here. Here's a quadrant. Here's up. The next one is the not strange. Here's the down, and here's the not charm. Then the opposites are on the other end. So this exactly mirrors that. It's just wrapped around the ball in 100 or 360 degrees. Then I realized that if I drew 4-dimensional lines this way going through those points, I got intersect points. And those intersect points are shown right here, and they created baryon octets. So there are 8 baryon octets on this ball. And you can see them up there, like right here. There's the not UUD, wherever those intersect points are, with the 4-dimensional lines with the 3-dimensional polar coordinates. This then creates, this would agree with Simone's electron-positron lattice then, because if you look here, go back to here, the up quark is 180 degrees out of phase with the down quark. So if you had an electromagnetic wave that was progressing through the ether, what you'd have is you would have an up quark an up quark by the red dot, and a down quark by the black dot. So you'd actually have an up, down, just as the wave progressed. So that would agree with Simone's electron-positron lattice. Now the difference is they're not electrons and positrons, they're virtual electrons and virtual positrons. They don't become one or the other until something forms. Then I was starting to look at the motion of the ether itself within the cell. And on the left, I've got a picture of a water wave. If you have a wave going by on the water and you look at the motion of the water itself, it forms a circle. So this is what I've done here. I've said, well, as this thing would go by, what you do is you get, this thing is, this is not a static, this is dynamic. This is always in motion, always moving. And that's what I'm showing here. If you see the arrow at the top, you see the green, red, blue, and black. This is like a gyroscope that's spinning like that. And there's motion then going on inside each one of these cells. So then I started looking at fractals. And the purpose of this fractal was to build outer loop, put inside of it identical inner loops. So every loop was identical. This particular one is an 11-loop fractal. So if you look within the outer loop, you'd see 11 identical loops inside, except they're just at a different scaling ratio. So then you can go through the math and you can calculate the scaling ratios. I highlighted one in red right here, which is the 11, and then I also highlighted 6, because we're going to talk about that one later. And that has a scaling ratio of 0.5, or reciprocal would be 2. And that's a very important one, the hexagonal fractal. So then I started looking at what these fractals would look like. So there's a first and second generation 11 twist loop fractal that I just showed you, and I'm following the actual energy lines around. That's what I'm doing here. If you notice the blue, there's red. Red goes around, now it goes to blue, and the blue goes around. It comes back to red, so it's one continuous line. Then I did that with another 11 inside those 11s. So now I have 121 loops. The same exact thing happens again. It's one continuous loop. It goes around, it jumps to the other side, goes around, jumps back to the first side, gets the other one, then jumps back to the second side, gets the other one, and then returns back to where it starts. And then this is just a picture of trying to make a 3D picture of what that fractal would look like. Now this is only 2 generations. This thing could go down to 7, 8, 9, 10 generations. The detail would be tremendous. There's no way I could possibly draw it. This is a 7 twist loop fractal. There's 7 circles inside. It was a little more difficult following the pathway through there, but I finally managed it, and it did the same thing. So I repeated it many times, and it worked the same. Then I found out you could do half. You could have 9.5. You didn't have to have even numbers. So this is actually 9.5 doubled is 19. There's actually 19 circles in there, and they're overlapped. You get 9.5 of them on one loop, and then 9.5 more on the second time around. And this is that fractal over here, then on the right. And now, this is the hexagonal fractal. The unique thing about the hexagonal fractal is that you have 6 loops, and inside those 6 loops you have 6 more loops, and inside of each one of those you have 6 more. And what happens in the center of it is you create a center fractal. Because they touch in the center, you actually get another fractal in the center. And I'll show you that here in the models now. In the models, what I was trying to do now was build the hexagonal fractal. And what I did is I took 3 balls and glued them together, and took 3 more balls and glued them together, and it went like this. And it was interesting because you now have polar coordinates. You have a polar coordinate that way, this way, and that way. And that's shown in this model right here. So then what I did next is I wanted to see the next generation. So I took 3 and 3 and put them together, and there's the, I'll get it set up here,
Just twisted, 6 degrees.
It'll go eventually. There it is. There is that's the octahedron. That's a pyramid octahedron, and that's 3 of these, 3 of those put together. So it's like, well, that's interesting. Again, you can see very clearly that you got 3 squares along polar coordinates. So that is this. Now, that's the same as this one and this one here. These 2 are identical, but this illustrates the 6 groups of 6 balls. There's 36 balls here. There's 36 here, but if you look in the center, you see the 6 yellow ones in the center. So this does exactly what the diagram said it would do, and it forms another fractal on the inside of it. Then, what I saw on the face was Sierpinski's triangle. And I thought, well, I need to do one more generation to see if that materializes. So there it is. And that's this one down here. And this got 216 balls in it. There's 6 groups of 36 in each one. The fractal forms in the middle, and you can clearly see that it is Sierpinski's triangle. It is the exact, each face is Sierpinski's triangle, and the entire structure is Sierpinski's pyramid. So the hexagonal fractal and Sierpinski's pyramid are one and the same. So now we have the math for this structure, and it correlates exactly with Sierpinski's triangle. So that lends some credibility to the fact that this has some potential. The question is, what is it? So then I decided, well, this structure is a four-dimensional structure that's got 3 dimensions polar axis in it. That was the same thing I had here. So what happens if I take these and put them into this? So that's what this is. This is 36 of them. And if you look and you'll see all the red lines line up, all the red lines on this polar coordinate line up, and all the red lines on that polar coordinate line up. Then if you look at the individual green lines, which are the string lines, all the green ones line up, all the yellow ones line up, all the black ones line up, and all the blue ones line up. So then I was able to take this thing, which I developed probably 20 years, which I developed 20 years ago, and incorporate it into this that I developed in the last 2 or 3 years. So that adds more credibility to the fact that this is correct. So then, okay, there's Sierpinski's pyramid on the left. And if you look at the red one is just the top half of the pyramid. The blue one shows the bottom half, and then you compare it to the structure, and you can see they're the same. That shows the correlation between the octahedron within the hexagonal fractal and the relationship to a cube, that they are dual polyhedral. Okay, now, this is something I did a couple years ago. I was looking to find out how we could correlate from an electron to a proton. And we had talked about using 7 layers of resolution, which is right here. And the problem you have is the proton is 1836 point, I can't read the number, 28, whatever, but it's an odd number. And you can't have that. You have to be able to explain what that odd number is. So what I found is by converting from a 3-loop mass explanation to a hexagonal mass, and I did that before this was even developed. I went to 6 loops, and then if I found out I went down to either 10 or 11 layers of resolution, and what I got is a ratio for the proton that now fell within the limits. In other words, if you look at this one, it's 46.3, and that's 52.6, 49 falls in between, and that falls within the known codata values for the ratio. So you have to have more resolution. The fine structure of the ether has to be smaller. It has to be at least 10 levels, preferably 11 levels. Then I started working on the Phi Pyramid. The Phi Pyramid, you look up here, it's a square inside of a square inside of a square. And from that, you see all kinds of square root of 3s, square root of 2s, square root of 5s, all kinds of interesting numbers. But what I did down here in the bottom is I took it and said, well, what happens if I stretch it out? You see the red one's, this black one is stretched out to red, or if I stretch it that way to blue. And then I went through the math and did the calculations, and what you come out with is phi. So from this pyramid, you can calculate phi. And the most interesting thing about phi is that the natural log of phi and of the 0.68 and 1.68 is identical. So if forces vary by the natural log, then this would be an equilibrium point for the ether structure. That could explain charge, because what happens is there would be 2 plateaus where the structure would find equilibrium. And that would be at either stretching it out or collapsing it, just like I had shown in the beginning of the charge. Then I started looking to try to find out if I could predict the mass of an electron or Planck's length from this structure. And I'm going to, the one I wrote up is based on a more complicated structure that you have to subtract 0.5 from every one of the 2's over here. You see 2, 4, 8, 16, 32, and I subtracted 5, calculated new ratios. That was based on this structure right here, trying to put a hexagonal fractal in the middle. You would repeat that 11 times, then you'd have a new center develop. And then you'd repeat it 11 more times to get down to Planck's length. That was the one solution over here. And that is to go with 2 through 11, and that when you multiply those out, you get 2047. Now, if you take the scaling factor of 2, and you just take 2 and take it to the 11th power, you get 2048. Planck's length is right around, there it is, 2046 is the number you need if you take the 7th root of it. What I'm going to show you right here is this number right here. The 77th root of Compton wavelength to Planck's length, that ratio, the 77th root of that is 1.999828. And the number we've been looking for is 2. It's a very close correlation. That is the one that operates on a straight, it just forms, takes 77 iterations of that pattern. This is 3. It would take 77 iterations. And if you take 2, and you take it to the 77th power, that would be very close to the ratio. It's 0.7% off. If I use the other method, it's 0.32% off right there. That's 0.69%. Then, that's what I'm showing you here is the 2 different versions. This is 77 layers where it just keeps growing out. This is this one over here on the right is 10 layers where it creates a new seed, grows 10 layers and creates a new seed. This is the one I calculated first because I thought that it was closer to Planck's length. It was only 0.32% off. This one was 0.67%. But now since we've evaluated both of them, I think this has the higher probability of being the correct one. So then what I did is I said, okay, now can I develop a structure for the proton? So I took the smallest ratio from the electron to the proton. I took the smallest electron and compared it to the biggest variation in the proton, and then I did it the other way, so I kind of calculated a range. Then I look at that range and I calculate how many cells, and simply all you're doing is if you have 2 to the 10th power, I'm looking at each generation. There's 7 generations. Each generation has either 10 or 11 layers in it. So there's either 60 million cells in an electron or 362, depending on which one of these 2 is right. I believe this is the correct one, the 362 million. Then what I do, and that's only to the 11th power, so that would be to the 7th power. You have to take that, and you get a number very close. You're going to see later on that Kellen had talked about where it was e to the 57th. You're going to see some numbers like that here pretty soon. So what I'm doing here is per generation. So what I did is I took the 7th root of 1836. That's this number. Multiplied times the number of cells to get the number of cells there would be in each generation of a proton. Then it's, well, can we build a proton that looks like that? So this is what I'm proposing a proton looks like. It's a loop. And if that loop was about the size of a basketball, it would be about the size of a 12-gauge wire. So it's a very small loop, is what a proton is. And it's made out of 857 loops. And I got that by taking the proton charge radius, converting to the charge radius circumference, dividing it by Planck's length, and then taking the 7th root of that. And I come up with 857. So I'm starting with 857. Now the question is, with 857 loops around in a rotation, how do I get the 1 billion cells that I need? So what you do is you take that number and you divide it by 857 right here. When you take that by 857, that tells you how many trips you need around. I'm going to skip ahead through some of this. Here we go. Here's the million. Divided by 857, you get how many trips there are per generation. So there are this many trips in each cell, 1.23 million. Now, I'm going to go to the next picture. Okay, this one here, this is easier to explain from here. When you divide that by the 857 in the one sequence, you come up with 206,445 with a remainder of 2. So what happens is that means that when you divide it by 857, you have to go around 206,445 times. So, but you have a remainder of 2. So what you do is you advance by 2. The remainder tells you what the advance is. So the first trip around, the loops are all on zeros, all the way around the loop. The next time around, they're all on the 2s. The next time the 4s. So we're getting all the even numbers. Then if you take the quotient of the division, which is this number, divide it by the remainder, that tells you the advance. So the advance then, advance is 2 there, and you do the odd numbers. So now when you get to the second cell, you've progressed up to this point. Out of that 857, you went around 206,445 times, and you've come back to where you started. Except you're 2 loops past where you started. So you take 206,445 times 857, and then subtract the 2 loops off. Because now you've progressed forward from here to there. And you're able to hit the mass ratio exactly right on the nose by doing that. Now here's another example. In this one here, I'm using the higher number, to the 77, and if there are a billion cells in this one, you divide it, you get a million per level. So there's got to be 1,238,670 in here. And the remainder on this one is 7. So the first 7th time you go around, you hit the zeros. The next time you hit the 7s. And the next time you hit the 14, then 21, 28. When you get to the very end, you find out that if you take the quotient, divide it by the remainder, you get it advances 1 again. So the next time then, after you do all this up to this point, then you do the 1s. Then you do the 2s, 3s, 4s, the 5s, and the 6s, and you finally get back to where you started here. And now you've advanced 7 cells. So you take 1,238,670 times 857, and then subtract the 7 cells off, and you're able to hit it directly on the nose again. So this structure would work for a proton. Now there are some limiting factors. Let's go back up here. When you divide the quotient by the remainder, it cannot be evenly divisible by the remainder nor by any prime number of that remainder. If it is, it truncates. It gets back to where it started before it makes all the loops. So that's what, for instance, if the remainder is 3, the quotient cannot be divisible by 3. If the remainder is 4, it cannot be divisible by 2 or 4. If the remainder is 5, it can. If it's 8, it could not be divisible by 2, 4, or 8. So over here, I applied that logic to this particular scenario to see which ones would work and which ones wouldn't work. And you can see there was 3 of them worked. The nominal one worked very well, which was the remainder of 7. This one wouldn't work right here because it's 6, and this is divisible by 2 because it's an even number. And if you add 1 more on, take 1 off, this one worked because it's divisible by 5. So there was a reason why none of those would work. Obviously, there's got to be more restrictions than just this. It still can't explain why the structure would form and not other ones. But it does show you that it is possible to build both an electron and a proton structure and hit the mass ratios directly on by going through fractals.
2 minutes.
Okay. Yeah, I'm done. That's pretty much it.
I'm sorry.
No, that's okay. That's fine. I was at the summary right now. So if anybody has any interest in any of this, I'll be around all week discussing it.
Can I just ask you a couple questions for clarification?
Sure.
And if anybody else wants to, we've got 2 minutes. I just want to clarify, when you're looking at your little loops going around, you know, you're saying that they're dynamic, what is it exactly that's moving? I mean, I don't think you clarified that.
I envision each of the energy cells as being the same structure as an electromagnetic wave. So if you go back to the rotating oscillating system, there's more I haven't talked about. If you take the quark ball and you look at the quark ball, on the down quark, on the opposite, there is a not down quark. Mm-hmm. So what I see right now is I see ether flowing back and forth as this thing goes through the ether. You see energy going from the left to the right, to the left to the right, and back and forth as this thing propagates forward and as it stands there. So, in both cases.
So are you seeing energy flow along those different colored paths in your ball?
Yes,
that's how
definitely.
you see it?
What I'm seeing, yes.
They're intersecting at those nodes, and those represent...
Right, and what I'm seeing, for instance, is when these blue ones come together, they're intersecting, and the energy is going like this, and it's coupling, so that these actually become one long string of energy. And this is not a static system. This is total dynamics. Everything in here is moving. Nothing is
But then what you're holding in your hands, what would that represent to you? Is that an atom?
Electron right here.
It's what?
That's an electron.
It's an electron.
That's an electron.
It's actually, the question follows up on his. Can you conceive of another something moving that has energy, or does you really require that energy itself is traveling from location to location within the electron?
The only thing I see the ether is all pure energy. Okay, what the ultimate final structure is of ether, I don't know, and I don't know if we will know, but I'm operating under the proposition that what Planck said was the smallest electromagnetic wave that you can have before the wave system collapses is the first energy cell. And then all mass structures are built from that point on. Okay.
So essentially, you feel that the ether is traveling, that is supplying the energy of the motion.
Yes. So what you have is that fundamental energy almost becomes like an excitation or a background energy that's making the ether move, and then the ether forms the cell, and then these cells go together and form the particles that we have.
And then one last question on the same area, if I may. Can you conceive of fields the ether being a field, and therefore the field traveling through it that carries the energy, because fields have energy?
It's definitely a field.
Okay, so then I can see how this relates with Don's last discussion a little more on that.
To me, what mass is captured energy.
Okay.
That's all it is. In other words, everything is energy. And what mass is captured energy. Once you get energy captured in a structure and it can't come apart, now we call it mass. But it's still pure energy. But it's just captured energy.
Okay, thank you.